So last time we started the chain rule, and this is actually what we looked at. So when we're taking the derivative of a composite function, we can either take the derivative of the outside and we rewrite the inside exactly like it was before, and then we take that multiplied by the derivative of the inside function. And we encountered a couple of examples, and then the third one we did actually looked like this. It's kind of messy, and the reason it's messy is in part because of the simplification, honestly. I mean, a big part of it's the simplification. But this is one of the ways to do it, and what we had done is we took everything with the fraction inside of it and raised it to a power. What I mentioned at the end of class last time is that we could have done it slightly differently. I don't know that it's necessarily any easier, it's just different. And so we can, instead of taking the entire inside raised to a power, we could apply that square root to the individual numerator and denominator and do it from that perspective. So I'd like to show you what that looks like, and so you can see whether or not you like that any better, basically. No, I don't have any more space. So what I'm going to do is I'm going to shrink this. See if I can, got to capture it all first. And we'll do the other method next. Okay, so I realize you can't read it, neither can I, but it's still there. All right, so we're going to try this from the right-hand perspective where I rewrote it over there and go from there. So as we look at that particular function, the way it's set up or described, we actually see that there's a quotient rule. There's something going on top, there's something going on bottom. So the quotient rule is our overall outside function. What's the quotient rule? Well, what is the quotient rule? Well, the quotient rule says, what was my function name? H prime of t. The quotient rule says that I take the denominator times the derivative of the numerator, right? So the denominator is 2t plus 3 to the 1/2. And I multiply that by the derivative of the numerator. All right, to be honest, there's no way this is going to stay here and actually work. So let me just shift it over, even though it's messing up what's on bottom. There we go. And then I need the derivative of the numerator. Now, the derivative of the numerator actually has a chain rule in it, right? Because the numerator itself has an inside, namely this part, that's raised to a power. So as I take the derivative of the numerator, I actually have to do the chain rule inside now of the quotient rule. So what does the chain rule look like? Well, I would take the derivative of the outside, which pulls down the 1/2. I rewrite the inside, 3t squared minus 2, and I take 1 less on the derivative's exponent. Is that good so far? I think I'm really just kidding myself that I can fit all this in. We're just going to cut it. All right, so that's the derivative of the outside of the numerator. Now I need the derivative of the inside of the numerator. What's the derivative of the inside of the numerator?
6t.
Good, 6t. It's half of the overall numerator of this quotient rule. Then I have a subtraction sign. Now I need the derivative of the denominator. Well, the derivative of the denominator is another chain rule. It's this piece to the power 1/2. So much like I just did before, I bring the 1/2 down. I rewrite the piece in red, 2t plus 3, and I decrease the power by 1. So decreasing 1/2 by 1 gives me negative 1/2, like we did before. And then I need the derivative of the inside. And what's the derivative of the inside? Just 2. And then I need this multiplied by the numerator, right? Derivative of the denominator times the numerator. And so I have 3t squared minus 2 to the 1/2. And all of this is over the denominator, 2t plus 3 to the 1/2 squared. So notice the denominator actually has a really nice feature because it has to the 1/2 squared, and those are going to cancel. My denominator is actually going to be 2t plus 3, at least for the moment. Does everybody catch that? Now, if you were doing your gateway on Friday, you'd stop right there and you'd be very thankful, right? But we're going to clean this up. And there's a lot to clean up in this one, just like there was in the method that I just erased. There's a lot to clean up. So let's take a look at how it would clean up if I was working with that. So first of all, notice, of course, the 2 and the 1/2 exponents here cancel.
So, I have one question.
Yeah.
You're putting the bottom first up there because you're like taking the 1/2 of it, like. I'm just confused because it looks like you're taking the denominator and then getting the derivative of both the denominator and the numerator and then subtracting it from the denominator.
Okay, so let me show you the 4 pieces that are happening in the numerator, and maybe that will help. So you're right, I did the denominator first. So the denominator is the 2t plus 3, okay? And then I have the derivative of the numerator, which is the 1/2 t squared minus so forth. Then there's my subtraction sign that I've circled in red. The other piece that has not changed by taking its derivative is the numerator piece, and it's at the very end here. Now, if you wanted to switch that and write that before you did the derivative of the denominator, you could do that. It doesn't matter.
I guess I'm confused why there's another 6t, because it looks like you already took the derivative.
This 6t right here,
Added 6t.
are you talking about that 6t that I just highlighted? Because it's the derivative of what's going on inside. It's the chain rule. What you see happening right here, I think we should use this, is the derivative of the numerator, and the derivative of the numerator is a chain rule. Okay, so the chain rule, which is the section we're in, says that I take the derivative of the outside, that's the bringing the 1/2 down and decreasing the power, and I leave the inside the same. And then I have to multiply that by the derivative of the inside. So there is 2 derivatives going on because there's a chain rule present, the derivative of the outside and the derivative of the inside. Okay? So I by no means am trying to trivialize this problem because this is a hard one. This is a very challenging problem. The simplification of it is atrocious. But even taking the derivative of it is very complicated because there's so many pieces going on.
Should be a negative 1/2 on the...
It should be a negative 1/2, yes. That's missing, thank you. Might have been, oh, it's because I shifted something. That negative got left when I shifted it, didn't it? I erased something, I wonder what it was. That's what it was. Too much moving around on my screen. Okay, everything else look okay? All right, good. So in terms of simplification, let me take that off. This 1/2 and this 6t can simplify. It's all multiplication, so I can write that as 3t. So I have the square root of 2t plus 3. I have that 1/2 and that 6t. I'll write that at the beginning. That's actually going to be 3t now. Oops. And then the piece here in the middle that we've been sort of talking around, the 3t squared minus 2 to the 1/2, is actually 1 over the square root of 3t squared minus 2, like that. Then I have my subtraction sign. So now we've got fractions inside of fractions. We will have to deal with that before we're done. The other piece, I see a 1/2 here and a 2 here. So those cancel out completely and very nicely at that fact. And then I have another denominator. So I have 1 over the square root of 2t plus 3. And then I have my square root of 3t squared minus 2. The denominator is now just 2t plus 3. And I don't really need the parentheses, but I'm going to put them there because I'm going to need them for some multiplication purposes in a minute anyway. Okay, is that okay so far? Okay, so fractions inside of fractions is definitely not simplified, all right? So I don't want those little denominator fractions that are happening right here to still be present. So how do I get them to not be there? Well, I actually will multiply by them. Okay, so I will multiply the numerator by each of them. So this is 3t squared minus 2 and 2t plus 3. But of course, if I do that to the numerator, I have to do it to the denominator, 3t squared minus 2 and square root of 2t plus 3, like that. Now, the numerator, when I do this, And actually, let me write this on the other side too, just because it'll be easier to show my simplifications. So I'm going to be multiplying here and here. So I've got this piece multiplied and this piece multiplied. So the whole point in doing so is that I'm going to be able to take this 3t squared minus 2 and cancel it with this 3t squared minus 2. Right? One's in the numerator, little numerator, and one's in the little denominator. So these two cancel. And then I'm going to be able to take this 2t plus 3, both here and here, and cancel them. Now, some other really nice things actually end up happening when I do that, because the other pieces that I'm multiplying, namely this 2t plus 3 has another 2t plus 3 underneath the radical it's being multiplied by. So those are going to combine super nice, right? They're just going to cancel out the radical part of it because I have the radical 2t plus 3 squared now. So the 3t is still at the beginning. I have 2t plus 3 next. And then I have the subtraction sign from the middle. So I'm sort of like all the way here. And then the same thing is going to happen on the other side. This piece and this piece are going to multiply together and collapse, right? Because I've got them squared and square rooted. So that's going to be 3t squared, minus 2. The numerator now will actually have no radicals in it, so that's lovely. It will simplify and condense very nicely. The denominator is kind of a wreck, but it's going to be a wreck when we're done. This is 2t plus 3 to the 1, and this is 2t plus 3 to the 1/2. So depending on whether or not you're leaving it in radical form, which we will, or whether you're turning it back into rational exponent form, you could combine that power of 1 and that power of 1/2 if you wanted it in rational exponent form. We don't actually. So our denominator, although it's kind of a wreck, doesn't have to actually be dealt with. We're going to have this 2t plus 3, and we're going to have each of the square roots. And they don't really matter what order they're in. I'll just leave them in the order I have them, which is 3t squared minus 2, and what was it else? 2t plus 3. Okay, so you got to admit at this point, this is significant improvement, right? It really is. And my numerator will clean up pretty nicely. So let's see what we have here. I have 6t squared plus 9t minus 3t squared minus 2. Oh, plus 2, yes. I didn't catch that. Thank you. And then the denominator stays the same. We're almost done. All right. How will the numerator simplify? Mm-hmm. Yep, the 6t squared and the 3t squared. So that's 3t squared plus my 9t plus 2. And while we would love to know, does it factor? We really only care if it cancels with something in the denominator, and it won't because I can't get, while I could get a 2t as opponent at the component at the beginning here, I can't get this one at the end, right? Because I can't have a factor of 3 when I have the number 2. So my last part is the square root of 3t squared.
How would you get a 3t at the beginning?
Minus 2.
A 2t at the beginning?
Actually, you couldn't. I was looking at my 6 when I said that. I apologize.
Oh, okay.
No, you're fine. I was on the wrong part of my screen. Yeah, so I can't get the factor 2t plus 3, and it fails in both ways. You're right. 2t plus 3. Okay, and I erased what was on there before, but hopefully it's still in your notes. Does that match what we did last time? Whew, that's really good. Because I didn't have this one written down at all.
Yeah.
Yeah? It's all good. Always nice when that happens. Okay, after that hard one, we're going to do some easier ones. Y'all ready? Like, please tell me they're not all like that. They're not all like that. So I'd like to mention several here where you don't necessarily, when you look at them, see the chain rule. So that's kind of the theme of the next couple of them here, is that the chain rule may not be automatically obvious unless you're really looking for it. So there is a chain rule here. But a lot of times the chain rule is easiest identified by some parentheses, and there aren't any parentheses in this problem, but there really are parentheses. They're just not written in. Do you know where the parentheses are supposed to be here? Yeah, around the pi x. If your calculator had you putting this function in, like you wanted to graph it or something, it would automatically put a parenthesis after the sign. And the reason that there's an automatic parenthesis or an understood parenthesis there is because the pi and the x, when multiplied together, or when they're beside each other, are understood to be multiplied together inside of sign. Okay? So my inside function here is pi x. My outside function is sine. So there's that derivative notation. We'll do the outside part. What's the derivative of sine? Cosine. And then inside, we rewrite the same thing. So the inside function never changes when I'm dealing with taking the derivative of the outside. Then I multiply by the derivative of the outside. I'm sorry, I said that wrong. The derivative of the inside. Yeah, so what's the derivative of pi x? It's just pi. Right? Pi is the coefficient of x, so the derivative of pi x is pi. There's really not a ton of simplification to do. We would typically see the pi written at the beginning and then the cosine pi x written second. Not super important kind of thing, but it clears up the fact that we want to make sure we understand that that pi is multiplied by cosine, not by pi x. Right? Okay, so that's why the pi is written at the beginning. This is another one where I don't exactly see any parentheses. There are parentheses, but there's actually two sets of parentheses. So can somebody tell me where you see one set of parentheses? Around the 3t. Yeah, that one very similar to our last problem, right? Around the pi x. Not square root, but the square. Okay, so last time you guys, I think it was in here, were asking me some questions like, do I have to put the square there? And I said, you don't have to. It's sort of a convention that we use. But this is actually meaning that I have the cosine of 3t, and I have all of it squared. And the notation where the square was before means that I don't have to use those parentheses, which is why it's a nice notation. But this is what squaring in that location means. It means the cosine function itself is being squared. So not only did I sort of have these missing parentheses, which makes this problem kind of like the last problem, I've got the pi x, now I have the 3t, that makes it similar. But on this problem, I actually have two inside functions. So what I have here is I have the chain rule that I'm going to have to apply twice. So I'm going to work from the outside in, right? I always start with the derivative of the outside. There is a 5 on the outside, but it just comes along for the ride. The power of 2 is the outside function, right? So what do I do when I have a power of 2 with an outside function? So in a very real sense, I've got, the orange blob thing from last time. What am I going to do with that power of 2? Multiply the 2 by the 5. Okay, so this is the derivative notation. And my 5 times my 2 is going to give me 10. And then I've got to the power 1. I'm going to write it for the moment. It'll go away in a minute, but just to remind ourselves we did that. And then the orange blob piece gets just dropped right in. It gets rewritten, cosine of 3t. So the outside-most function here is a power rule, power of 2. Working my way inside next, I'm dealing with the cosine of 3t. There is still another inside to that. So again, thinking orange blob, right? I've got my cosine function. So what's the derivative of cosine? Negative sign. So out here behind this, multiplied with the parenthesis to clearly indicate that we're multiplying, not subtracting, I have negative sign. But I have negative sign of orange blob, and orange blob in this case is 3t. And then finally I have 3, because that's the derivative of the 3t part. Okay? So there's a series of embedded functions here that I have to deal with. So I did the chain rule twice. Cleaning this up isn't too bad. I've got the 10 here, I've got a negative here, and I've got a 3 here. So that's negative 30. My cosine is actually to the power of 1, right? The cosine 3t, so I don't really need that power of 1. So it's really just the cosine of 3t, sine of 3t. And that took care of all my pieces.
So on the gateway, we would write the middle line, right?
Yes, this is where you would stop on your gateway. You would need to be very careful to have those parentheses in there, right, to indicate that it's not subtraction, it's really multiplication. That's important. I will count you wrong if the parentheses are not there because it means something different. I wouldn't count you wrong. You didn't have the power of 1. That's inconsequential at all. But the other part you would need. Any questions on that one? Okay, let's try another one. Now this one's a little bit different. For one piece, it's a little bit different because I have the 3x at the beginning and it doesn't involve the chain rule. So I've got a mixture here of something that doesn't use the chain rule and something that does. That's okay, we can do that. The part that does involve the chain rule, though, is not quite the same as the last problem. What's being squared here? The pi x, right? Not the trig function cosine. Cosine is not squared here, pi x is. So you can do this in a couple of ways. If you want, you can actually simplify this to say that this is pi squared x squared, like that. The reason that might be pretty handy is because that eliminates having two inside functions, because you've actually simplified what's inside that's being squared. If you don't do that, then you have, just like the last problem, two inside functions. You have the cosine, where we have to take the derivative, and then you're going to have to take the derivative of the pi x squared, and then you're going to have to take the derivative of the pi x. Right? There's more going on. So let me show you, because neither one of them take very long, that you get the same thing either way. So let's actually deal with it as though we didn't do that simplification, so you can see that chain rule applied twice again. Okay, so to start with, the derivative of the 3x, that one's easy. It's 3. And then over here, we have the derivative where we have the 5 cosine. That's the outside part. So the inside here is the pi x squared. Okay, so what's the derivative of 5 cosine of something? Right, it's negative 5 sine. So there's a subtraction, and then I have a negative 5 sine, and it's of pi x squared. Okay, so far so good? That's the derivative of the outside. The outside right now is the cosine part. Now I need the derivative of the pi x squared. Well, the inside there is the pi x. The outside's the 2. So the 2 is going to come down. And I'm going to have that same pi x to the power of 1. And then I need the derivative of pi x, which is pi. Okay, this would be one way to write the derivative. We'll clean it up, and then I'll show you the other way to write the derivative. So on this, let's see, we have 3 plus 5 sine pi x squared. And then I have 2 times pi x times pi. So the 2 can get grouped in front, actually all of that can be grouped in front with my 5. So 2 times my 5 would be 10. And then I have the 2 pi's, so that's pi squared and x. So I did the chain rule twice. If I recognized that I could simplify that inner piece, and I did write it as pi squared x squared, that would be my other option. I still have the same piece at the beginning, 3. I still have minus, and then I would have another negative 5 sine, and it would be pi squared x squared. And then I would have the derivative of pi squared x squared. Okay, well, pi squared is my coefficient, so just ignore that for the moment. The derivative of x squared is 2x. So I would have the pi squared and times 2x. So pi squared, because it's a coefficient, and then 2x. And you'll notice I have all the same pieces I had before. There's the 2x, there's my pi squared, and there's my positive 5. So So there's my 3 plus 5 sine. Oops, I'm sorry. Didn't want that. I wanted to combine them. 3 plus, and then 10 pi squared x, and then sine of pi squared x squared. And that's the same as the problem above. I've just got the pi squared x squared written in this distributed form, basically, instead of in the factored form here. But that's the same otherwise. Okay, any questions on that one? Okay. Our last couple have some additional instructions afterwards beyond just find the derivative. Your gateway on Friday just is going to be find the derivative, find the derivative, find the derivative, and you don't simplify anything. These have a few extra directions. It says to evaluate the derivative of the function at the given point, and then we're going to verify it with the calculator. And I think I got the document camera working for us to check it out today too, and make sure that it's working for everybody to see the calculator correctly. So on this one, the first thing we're going to do is we're going to find the derivative of 5 over x cubed minus 2. Now you can either do it with a quotient rule, and that's fine, or you can bring the x cubed minus 2 up to the numerator and do it with the chain rule. Since we're practicing chain rule in this section, that's how I'm going to do it, but you'll get the same answer either way, okay? So I'm going to rewrite this first as 5x cubed minus 2 to the negative 1. So what will I get for my outside derivative? Negative 5 into the negative 2, right? The inside stays the same, so that's x cubed minus 2. And then I need it times the derivative of the inside. So what's the derivative of the inside? 3x squared. Okay, so if I were on the gateway, I'd be done at that point. And then this problem, though, wants me to evaluate it. I want to simplify a little bit before I evaluate because it'll probably make my evaluation a little bit cleaner. I have this negative 5 and I have this 3x squared. So that's negative 15x squared. And then that negative exponent means I'll take that x cubed minus 2 back to the denominator and make it squared. So that's the simplified version of the derivative. And now I want to evaluate it at the x value of 2. Your book likes to give you the ordered pair, like the point on the graph where it's doing it. The only part that matters for evaluation purposes is the x value for now. So, negative 2. Yeah, we'll fix that. All right, so I have negative 15, negative 2 squared. I have negative 2 cubed minus 2 to the power of 2. So on top, let's see, that gives me 4 times 15, I think that's negative 60 on top. On the bottom, I have negative 8 minus 2, that's negative 10 squared would be 100. So I think this gives me negative 3/5. Is that right? Okay, so negative 3/5 would be my my solution. The part where it talks about the calculator verifying, which is not useful for anything related to Gateway, but let's just pause for a second and take a look at your calculator and remind you how you can verify with it. Still upside down. That's not working. I played with just getting it to work, not getting it to display right. I just need to move me. Might be my best bet at this point. Okay, so in your y equals, you're going to put the original equation. You can write it just like it is on the actual problem. So 5 over x cubed minus 2, or you can write it how we changed it. So I've got mine written. Oh, I put it in the y2, not that it matters, but we'll fix it. Okay, so there's my function written in my calculator. If you'll remember, you exit out to the regular screen, and then you use the button that says Math, and it's option number 8. So it'll either look like this, or I'll borrow somebody's in a second that looks different. But if yours looks like this, you tell it vars, y-vars function y1, put a comma x, and then a comma with your -2 value you're inputting. And it should give us -0.6, which was -3/5.
Wait, you do vars?
Yeah, you go to get that thing to show up, you do math 8, and then it's vars. You go over here to y-vars. It's a y variable, vars is variables, okay? And then we have function and y1. You do the comma right here with x, and then comma and -2. If you have this version, which Callie's letting me borrow, oh, I've got to move the screen or it's too bright for me to be showing both at the same time because they're so different. Okay, that's not too bad. It'll pull up looking like this instead. So you have to actually tell it the values that you want. So you're going to put in an x here because it's the derivative with respect to x. Over here you tell it y1. You get that by doing vars, y-vars, function y1, same as the other one. And then over here you let it say -2. She'd already entered hers. Once you press enter, it'll do the same thing. It'll give you the same decimal approximation. Second. F4?
F4, the trace.
Oh, okay.
That's right. Alpha. It's
There, I already hit the alpha.
the alpha trace.
Oh, there you go. Is that just on this version?
I don't know. It's
I don't think I have an. I don't. What do I do? I don't think it works on my system. Maybe there's a different keystroke. Okay, let me give you back a calculator, Callie. All right, we have one more problem to take a look at. So let's do that and see how it changes the question, because it does change the question a little bit, another version of what we could be asked. So our last question asks us to actually find an equation of a tangent line, which we've done before. And then we're going to use our calculator to verify it. So I'll be able to use the document camera to show this one as well. But to start with, in order to find a tangent line, we need the slope. And the slope is the derivative evaluated at our point. So we're going to find our slope, or our derivative, of this function. Now this is an example of one that if you wanted to multiply it out, it would not be bad, right? This isn't a power of 5 on the outside, right? Like that first one we did last time. It's power 2. You could so square this if you wanted to and use simple rules. It would be totally fine. We're in the section where we're practicing chain rule, so we're going to do the chain rule. So the chain rule with this says that I'm going to bring my 2 down. I'm going to rewrite the inside and decrease the power 2 by 1. And then I need the derivative of the inside. So what's the derivative of 4x cubed plus 2?
12x squared.
Fabulous. 12x squared. And if you're in the gateway, you'd be done there.
Isn't plus 3 works?
It won't be plus 3. So why will it not be plus 3? Oh, you mean here? So sorry. I thought you meant in the derivative. You're right. Plus 3. Thanks for catching that. Okay, is that good? Lovely. And then to simplify, we can multiply our 2 times our 12x squared, which gives me 24x squared. And then I have this times 4x cubed plus 3. If you wanted to multiply this out, right, to keep simplifying, you most certainly could. It wouldn't be anything that you couldn't handle. This gives you 96x to the 5th plus, is it 72x squared? I think that's right. You can do all of that, but you could actually, if you wanted to on this problem, just stop right here and continue with the question you were asked, because it didn't really say find the derivative, right? We're only doing that because we need it in order to answer the next part of the question, which is to find the slope and then create the tangent line. So in any of these points through here, you could stop and you could actually evaluate this at the x equal to -1 value at any of those points. Since we went ahead and did it all the way out, we're going to use the last one, but it doesn't make any difference which one you use. So if I'm going to evaluate, and I'll put this in sort of that function notation, I'm going to put -1 in for all my x's. And the last one, because it's squared, means that it will just become 1. So this ends up being plus 72. The first one, because it's to the power of 5th, will means it'll stay -1, so I've got -56. So 96. I said 56. I don't know. 96, that's what I wrote. Yeah, it's 96. And then -96 and positive 72 is -24. So this is my slope, m, for my line that I'm looking for. And I have a point. My point up here is the -1, 1. So slope-intercept form of a line is y minus y1 equals m times x minus x1. The y1 value is 1. The slope value is -24. And the x1 value is actually a -1, so opposite of -1 or +1 in there. Simplifying, this gives me -24x minus 24. Adding my 1 makes it minus 23. So y equals -24x minus 23. So this is the answer, if you will, to part A, the slope of the tangent line. For part B, we're going to actually use a calculator, and we're going to graph the original function, this one, and we're going to graph its derivative that we just found in part A. So one of them in y1 and one of them in y2. Let's do that together. So in y1, I have the 4x to the 3rd plus 3 squared. And then the tangent line that we found was -24x minus 23. And we should be able to graph this. So I have, I'm just going to put it in a standard window. It's probably not going to be great, but we'll give it a shot. So zoom 6 is the standard window. Yeah, that's pretty bad. It's a parabola. That's what it graphed first, but it's very, very narrow. It's really tight inside here. So what we might want to do instead is to limit our x values. So if I hit my my window button and not make my window go from -10 to 10, because that's way bigger than I need, maybe like -3 to 3. It'll spread it out a little bit better, and I can see, oh look, it's not even like a parabola shape. I've got this little loop-de-loop going on up there that I couldn't see at all before, right? And you see that tangent line coming down here. That tangent line is coming down here at the point -1, 1. So -1 is the x value here, and then 1 is a little bit tiny up here, just barely. So my image actually looks a little bit different than what I thought it looked like initially from my first screen. So if I'm doing this on like a test, let's say, and I'm asked to verify this with Calculator Grapher, right? What you're going to be doing for me on that would be to actually draw the picture. So you're going to draw what your calculator showed you. And we're wanting for it to look, you know, approximately, right? So it looks something like that if we zoomed around enough, right? If we played with it enough. And the other line itself would look something like this. Okay, so I do in fact have visually what appears to be a tangent line with those pieces entered in there. Any questions on that? All right.